Welcome you all in the 18th lecture of Electronics Measurement and Instrumentation. In this lecture I will cover what is the wattmeter, what are the working principle of the wattmeter and application, advantage, disadvantage of the wattmeter and the type of the wattmeters. So, in this lecture I will cover wattmeter. So, basically wattmeters are of two types, one is electrodynamometer wattmeter and other is induction type wattmeter. In this lecture I will cover the basics of wattmeter and electrodynamometer type of wattmeter, the construction working of electrodynamometer type wattmeter, derivation of deflection torque, what are the different cause of error in this instrument and advantage, disadvantage and application of the electrodynamometer type wattmeter. So, the power measurement, what is electrical power? Electrical power is the rate of doing work and it is expressed in watt. When the power is more, we can express it as in kilowatt and megawatt. So, power P watt is equal to VI cos phi, where phi is the angle between the voltage and current. That is, a power of 1 watt is said to be expended or expressed when a source of 1 volt passes a current of 1 ampere through a load resistance or the impedance of 1 ohm at unity power factor. The electrical power is of three type. First is the real power. So, what is the real power? Real power is the power consumed by a resistive load on the system. It is expressed in watt. It is also referred as true power, absolute power and average power. Next is reactive power. Reactive power is the power consumed by a reactive load on the system. It is expressed in reactive volt amperes. Now, next is the apparent power. So, apparent power is basically the vector sum of the above two power component, as we can see in the diagram. So, in the diagram we can see that there is a real power and there is a reactive power. The vector sum of these are the apparent power. So, if in apparent power, if the deviation from its unity, if the deviation from real power to reactive power is more, then the apparent power is more. It means we do not prefer the power factor more than unity value. If the power factor is of unity value, then it means there is no difference between the real power and the apparent power. So, for this reason the cos phi should be 1 as possible. So, here from this triangle we can find out that VA square is equal to W square plus VAR square, and this power measurement, the consumption of power of any instrument or any machine can be measured by the wattmeter. So, wattmeter is an instrument that is used for the measurement of amount of power flowing through a circuit, and by this wattmeter we can estimate the electrical load of any system. This wattmeter is also important when we are using the power electronic circuits, because by this wattmeter we can measure, monitor and control power flow in the power electronic circuit. Now, wattmeter consists of two coils. Generally, wattmeter consists of two coils, one is current coil and other is voltage or pressure, or it is also known as potential coil. So, current coil is generally connected in series of the circuit and it carries the load current, and this current coil, since it is connected in series, so it should have very low resistance, because so that it can pass all the current which is flowing from source to load. So, current coil has only 2 or 3 turns of thick wire and hence it has very low resistance. We know that R is equal to rho L by A. So, if the cross sectional area is more, then the resistance is low. So, the current coil is thick and it is connected in series. So, its cross sectional area is more. Similarly, voltage or pressure coil is connected across the load circuit. Since it is connected across the load circuit, and the purpose of using wattmeter is that the whole current flows through the load circuit. So, and we do not prefer that the current is flowing through the this pressure coil. So, the pressure coil which is connected across the load, and hence the cross sectional area of the pressure coil should be very low, so that its resistance should be very high, again R is equal to rho L by A. So, if cross sectional area is less, then resistance is very high and no current will flow through the pressure coil. So, whole current will flow through the load coil. Since pressure coil is connected across the load, so the current which is flowing through the load is proportional to the load voltage, and this has a wound of several turns of thin wire, and hence it offers very high resistance. Since it offers very high resistance, the component the angle between the resistance the voltage and current is 90 degree. So, key point related to wattmeter. Wattmeter displays the electric power of a device. By this wattmeter we can monitor the power consumption, and we can also measure the voltage, current, power, power factor and energy consumption with an accuracy of 1 to 5%. Wattmeter is damaged if we use excessive current. So, the current rating is shown at the wattmeter. So, if the current is more than that rating, then it will damage the wattmeter. Wattmeter also, since it draws current, it consumes energy, and so but although the consumption of energy is very little, but yes, it consumes energy. Then they are available in electrical and digital forms. Now, type of wattmeter. Generally, two types of wattmeters are in use. One is electrodynamometer wattmeter and second is induction wattmeter. Electrodynamometer wattmeter can be used for AC and DC power measurement, but induction type wattmeter is not used for the DC measurement. Electrodynamo type wattmeter works on dynamometer principle. That means ki if two current coils are placed in nearby, then a force, mechanical force acts between these two current coils. So, if we keep one current coil, one coil fixed and second coil movable, then second coil since mechanical force acts between these two, the one coil will move, and if the indicator is attached with that moving coil, then that show the power. Then the most common application of electrodynamo type wattmeter is electric motors and generators, measurement of power in electric motors and generators. Induction type wattmeter is used for AC applications only, and it is based on the electromagnetic induction principle. In this wattmeter, two magnets are placed. In between two magnets there is a small very light aluminum disc is placed, and because of the eddy current flowing in the aluminum disc, the disc moves, and if the indicator is connected with the disc, it will show the power. So, this dynamometer type induction type wattmeter is used for the electric power measurement, control system, quality testing, etc. Now, in this lecture I will cover only the electrodynamometer type wattmeter, and in next lecture I will cover the induction type wattmeter. So, before going to construction and working of electrodynamometer type instrument, first of all we have to see what is the basic principle of electrodynamo type instrument. So, any electrodynamo type instrument consists of following parts like two fixed coil, moving coil, control spring, damping device and magnetic shielding arrangement. So, as we see in the diagram, it has two fixed coil, and in between these two fixed coil there is a moving coil, and the pointer is attached with this moving coil. So, fixed coil it is of two part. So, fixed coil is divided into two sections so that it can generate uniform magnetic field. Further splitting of this fixed coil in two sections facilitate passage of moving part in between them. The magnetic field produced by the fixed coil is very weak because it is air cooled coil. since the magnetic field produced by this fixed coil is very weak, that's why we need a magnetic shielding arrangement for the electrodynamometer type of instrument. Otherwise, if there is any magnetic field which is not inside the instrument but outer of the instrument, so that will affect the performance of the electrodynamo type instrument. Now, moving coil is generally wound on a non-magnetic metallic frame, then damping. When any instrument, when the needle is moving, when there is a deflection torque, and due to deflection torque the needle moves. When needle moves, then to stabilize this needle position, because it is vibrating, before stop it will vibrate. So, to stop vibration of this needle, we need a damping technique. So, here air friction damping is done. In air friction damping, a pair of aluminum vane is attached to the spindle, attached with the pointer is there. So, the end of the pointer is an aluminum vane is connected there, and that vane move in a sector shaped chamber. So, that provide the stop of the pointer at a position. So, it stops basically vibration of the pointer. Then yes, magnetic shielding is required, because the magnetic field produced by the coils are very weak, in order of 0.005 to 0.006 Weber per meter square. So, shielding is also required. So, to protect the instrument from the effect of external magnetic field, instrument is enclosed in a high permittivity alloy. Then next is control. We know that if small power is applied and if there is no controlling torque developed in the instrument, then the needle will not show the exact value of the power. If a small power is applied, then it will give the full scale deflection. So, to give the deflection proportional to the wattage, control springs control torque is required. So, in this instrument the control torque is provided by the control springs. So, there are two control springs which is connected with the current coil, moving coil, and they provide the controlling torque. So, these springs also acts as a lead to the moving coil. So, it is connected with the moving coil also. So, now this is the electrodynamometer instrument which acts as a ammeter and voltmeter. So, we can see that the moving coil, these two fixed coil and the moving coil all are connected in series, and this, because it is we are going to use it as a ammeter. So, it is connected in series with the load. When we want to use this electrodynamometer type instrument as a voltmeter, so as we can see here, these coils are connected in series, but they are placed parallel to the load, so that it can measure the voltage across the load. Now, the deflecting torque that is produced in a normal electrodynamometer type electromagneto type instrument. So, suppose here we can see that the current passing through fixed coil is I1 and current passing through moving coil is I2, and a resistance is also placed connected with the moving coil. So, if current I1 is passing over here, so let the current passing through fixed and moving coil is I1, I2 respectively, then the force, field strength, and hence flux density is proportional to I1. So, here B is equal to K into I1, where K is a constant. Now, the force on each coil, each side of the moving coil is NB I2 into L, as we have already studied in moving coil instruments. So, second is torque produced on the whole of the coil, because L is the length of coil, I2 is the current in the moving coil. So, it is NB I2 L, and this force acts both sides of the moving coil. So, the coil width is B. So, it is NB I2 A. A is the cross sectional area of the coil. Now, the TD, that is the deflection coil, that we can write like NK I1 I2 into A. So, here NK and A are the constant quantity I2, and so TD is proportional to I1 into I2, and here the this is the deflecting torque, and that deflecting torque is balanced by the control torque. So, controlling is provided by the spring here. So, Tc is equal to K2 theta. This theta is the angular deflection and K2 is the spring constant, and at equilibrium state, when equilibrium state appears, then only the pointer will stay at that position. So, that means the controlling torque and deflection torque both are same at that point. So, here we can see theta, that is the movement of needle, make the theta. So, theta will be proportional to I1 and I2. So, this is the general deflection torque equation for any electrodynamometer type of instrument. Now, we will discuss the electrodynamometer type wattmeter. So, electrodynamometer type wattmeter again consists of two fixed coil and one moving coil. Moving coil is since we want to make moving coil more resistive, so a series resistance is used. So, here we can see a series resistance is connected to the moving coil. The moving coil is connected across load, and hence we know we want very less current should flow through the moving coil, and so and it also carries the current which is proportional to the voltage across the load. The fixed coil is the current coil of the voltmeter, and the moving coil is the voltage coil of the voltmeter, and a very high non-inductive resistance R is placed in series with the moving coil to limit the current. Now, in this instrument, as I have discussed already, the controlling torque is provided by two control springs and the damping is provided by the air friction damping. In this instrument, eddy current damping is not used. Eddy current damping is used in the induction type wattmeter. Now, because of the current in the two coil, a mechanical force acts between them, due to which the moving coil, that is potential coil, moves, and hence the pointer attached to it also moves. The pointer comes in the rest at a position where the deflection torque is controlled by the controlling torque. So, this is the structural view of this instrument. Here we can see these are the two magnets, and in between them current coil is placed, and the moving coil is placed, and moving coil is also connected with the pointer. Now, deflecting torque. We have to find out the relationship between the deflecting torque and the current and voltage, that is we want to measure power. So, whether the deflecting torque is proportional to power or not. So, electrodynamometer instrument used for AC and DC both. So, here we can see that IC is the instantaneous value of current in current coil, IP is the instantaneous value of current in pressure coil, M is the mutual inductance between two coils, theta is a steady final deflection of the instrument, K is a spring constant, and V and I is the RMS value of voltage and current in the measuring circuit, and RP is the pressure coil resistance. So, now the instantaneous voltage across pressure coil is V is equal to root 2 V sin omega 2, because it is the instantaneous voltage. So, it is root 2 into V max. Since we have applied sinusoidal waveform, so it is V sin omega t. Now, since the pressure coil is very high resistance, pressure coil is made very high resistive, so it can treat as pure resistance. Therefore, the current IP, the current through pressure coil, is in phase with the pressure coil voltage, and the instantaneous current in the pressure coil is IP, and this IP is equivalent to root 2 V by RP sin omega t. Okay. So, now the instantaneous current in the current coil. Now, in the current coil, IC is equal to root 2 I sin omega t minus phi, because current coil is not a resistive coil, it is inductive. So, because of inductive nature, it will produce some phase difference. So, it is omega t minus phi. Now, where I, V and I be the RMS value of the voltage and current being measured. Now, instantaneous torque Ti is now Ic into Ip dm by dt. Now, we have to substitute the value of Ic and Ip in this from the here. So, it is root 2 I sin omega t minus phi root 2 Ip sin omega t dm by dt. So, when we multiply it root 2 it is 2 I Ip here in place of I have placed in place of Ic, I have placed I because the Ic is approximately equivalent to I, because there is very less current in the pressure coil. So, I Ip sin omega t minus theta sin omega t dm by dt. Now, here we can apply a formula sin A into sin B is equal to half cos A minus B plus cos A plus B. So, by this formula it will be I Ip cos phi, this is cos A plus B. So, cos omega t minus phi plus cos omega t cos A minus B. So, omega t minus phi minus omega t will be cancelled out, and here will be cos phi, and next is minus cos 2 omega t phi dm by dt. Now, this is the instantaneous torque. In AC current, since value is changing continuously, so we are not interested in instantaneous torque. We are interested in the power measured in a certain time period. So, we can measure the average power of the this AC signal, because AC signal is keep changing. So, if we measure voltage, if we measure power, instantaneous power at any time, so it will not give the exact value of the power. So, we are interested in the average power. So, average power is, we can integrate this for a time period of pi, for one cycle we can integrate. So, here integration is done for the average deflection, T d is equal to 1 by T 0 to T T I d omega t. So, it is 1 by T, and when we integrate it and we substitute the value of 0 to pi we are integrating. So, if we substitute the value, then we will get I Ip cos phi dm dt. So, Ip is equal to V by Rp, Rp is constant and cos phi, so it is I V cos phi and other quantities are constant. Now, this is controlling torque, we know Ic is equal to Tc is equal to k theta, and k is constant and theta is the deflection. So, final study deflection. So, theta is equal to we can place Tc is equal to Td. So, theta is equal to I Ip cos phi dm by dt k. So, it is Vi cos phi. So, Vi cos phi is the power. So, this theta is basically proportional to the power measured. So, by this is the constant term. So, P is the power, and so by this instrument the deflection is proportional to the power measured, and this instrument is having a uniform scale for approximately from middle it is for 40 degree plus minus, it is having a uniform scale. So, error in electrodynamometer type instrument. Errors are caused due to the pressure coil. Also, we have considered that pressure coil is resistive in nature, but since there is number of turns, so it produces some inductance. Similarly, the resistance value is very high, so it also produces some capacitance. So, because of this resistance and capacitance, there are some errors. Similarly, mutual inductance error is there. Then connection, whether we connect power pressure coil after current coil. If we connect the pressure coil, suppose we connect the pressure coil here and then after the current coil. So, what will happen, and there is a load. So, it means the current that is flowing to current coil is also some part of this is flowing to pressure coil. So, it means ki the current that we want, that will not in the load the whole current is not flowing, some part of the current is flowing to the pressure coil. Similarly, if we connect pressure coil before the current coil, then the voltage measured by the pressure coil is not the exact voltage that appears across the load. So, there is a so some of the power loss is because of this. Then eddy current loss is also there, vibration of moving system also creates some loss. Then temperature error is there because we are using a spring here, so spring constant is changing with the temperature change. Similarly, stray magnetic field is also affects the this performance of the instrument. Now advantage, because with this instrument we can use in AC and DC, and they are free from eddy current and hysteresis loss because we are not using a damping, electromagnetic damping. And this we can use accurate measurement of RMS value, whether irrespective of the waveform, whether it is triangular waveform, sine waveform, cosine waveform, it will give the exact RMS value. And precision accuracy is also same. So, if we measure the AC or DC quantity, it will give the accurate value of that. Disadvantage, this instrument have after some portion of time it has a square law response. So, the scale is not uniform, and it also has a since there is a moving part. So, it is also having a torque oblique weight ratio. So, fractional error should be there, and it is more costly than the permanent magnet moving coil or moving iron instrument. It also consumes power which is comparably high, and this stray magnetic effect is there. So, to prevent this, the instrument should be enclosed in a soft iron case. At low power factor, a serious error may appear in this instrument. Now, the uses of wattmeter. Wattmeter is used to record the amount of electricity and energy their customer. Suppose we have purchased any instrument and we want to find out what power it will consume. So, we can measure the wattage of that instrument. We can measure can also measure the small scale photovoltaic errors to determine the amount of electrical energy generated by them. We can also measure the power output of a motor to determine whether the motor is functioning properly or not. Wattmeter is also used to monitor the power consumption and other things. So, in this lecture I have covered the electrodynamometer type of instrument. In next lecture I will cover the induction type of wattmeters and the measurement of power in 3 phase circuits. So, thank you all.